the second rule that we use while writing electronic configuration is Hund's rule of maximum multiplicity, right? In fact, we have already come across this particular rule when we discussed filling up electrons into the orbital. You know, according to Hund's rule, whenever degenerated orbitals are available, okay, here itself would actually like to clear this. Degenerated orbitals, nothing but orbitals having the same energy, right? Like for example, the 3p orbitals. 3p orbitals, 5d orbitals, 7f orbitals. You know, all these orbitals except the one s orbital. Of course, there is only one orbital in s sublevel. But coming to the other three, p orbitals, d orbitals, and f orbitals, you know, in the absence of magnetic field, all of them possess the same energy. Okay, in the absence of magnetic field, all of them possess same energy, so they are called degenerated orbitals. You know, whenever degenerated orbitals are available, pairing of electrons takes place only after all the available orbitals are filled with one electron each. This is very interesting. The other day I told you, pairing of electrons occurs once the orbitals are filled with one electron each. Let me show you that. And remember, with one electron, you have to fill up the orbitals, and those electrons have to have the same spin. So orbitals are filled with one electron each, having parallel spin. This is the most important one. What do you mean by having parallel spin? Having the same spin. Let us take the 3p orbitals in the p sublevel. I told you that you need to fill up one electron each in the orbitals. Then only pair up them. Okay. So pairing occurs only after all the available orbitals are filled with one electron each. Right? You know, it can be this. This is okay. You go. Next. coming to the second one, they can even be this. Say these three have got the same spin. I mean clockwise spin. Even these three have got the same spin. They've got the anti-clockwise spin. They are okay, but this one is not okay. Check this out. One, this, and then this. No, this is not okay because this one has got a different spin, isn't it? So this is what I want to say. Parallel spin means having the same spin. This is what Hund's rule of maximum multiplicity says. Okay. Now coming to this rule, it is very clear that you cannot write the electrons into different orbitals just like that. You have to fill up one electron in each of the degenerated orbitals that are available. Okay. Next, once you fill up all the orbitals with electrons having parallel spins, so this is little bit important. Having parallel spin, in the sense having the same spin. Look at this. Either you can have all three with the same spin, I mean clockwise or anti-clockwise, but you cannot have this kind of an arrangement, kind of filling. First, fill up the orbitals, all the available orbitals with one electron each, then just go for this kind of pairing, isn't it? So this is what Hund's rule of maximum multiplicity says. Okay. Next. Let us go for the third one that we use in writing the electronic configuration, that is Pauli's exclusion principle. Okay, what is this? You know, according to, yes, Pauli's rule, no two electrons in an atom can have the same set of 4 quantum numbers. See, I told you principal quantum number, even azimuthal quantum number also. There is a magnetic quantum number and there is a spin quantum number. So these are the 4 different quantum numbers that we have. This is, of course, principal. We'll discuss in detail about all these later. Azimuthal, then this is magnetic, and this, of course, is spin quantum. But what I would like to say is the same thing can be given in a simple way, saying an orbital can accommodate a maximum of 2 electrons. I mean, you cannot accommodate more than 2 electrons in an orbital. Look at this. This is okay. This is okay. But you cannot write more than 2 electrons. If at all it is written, then the first one and the third one of course, will have the same set of quantum numbers. So that is the reason why you cannot write more than 2 electrons in an orbital. So this actually restricts the maximum number of electrons in an orbital to 2. Not more than 2 can be written in an orbital. Is that okay? So this is Pauli's exclusion principle. So with this, I've actually given you 3 different principles. One is Aufbau, the other one is Kunz. Next, this is Pauli. Now let me also tell you the methods of writing electronic configuration. After that, we'll go for the electronic configurations of all the elements. Now, see, I have 4 different types of writing electronic configuration. The first one is NLX method. You know what N is? N is a principal quantum number, right? L is azimuthal quantum number. Of course, principal quantum number N refers to the orbit, whereas azimuthal quantum number L refers to the suborbit or sublevel. I told you this. Now, what does this X refer to? It refers to the number of electrons that are accommodated in a sublevel. Now, let me give you an example. Onto this side. Let us take carbon. You know the atomic number of carbon is. We'll of course go for the electronic configuration of all. But for now, look at this example carefully. Atomic number, which is represented by Z. The symbol of carbon is a C. You all know that. Atomic number of carbon is 6. Now, when you write the electronic configuration as per this NLX method, I told you that the first sublevel or the first orbital that is filled up is 1s according to Euler's. I hope you all remember. Let us write 2 electrons in 1s orbital because you cannot place more than 2. After 1s, you know you have to go for 2s. That's it. We are left with 2 more electrons. Then they can be accommodated in 2p. Hope you all remember. As per Euler's, the one with the least energy is 1s, then 2s, then 2p. Right? So look at the things here. This refers to n, and this refers to azimuthal quantum number. Of course, here in this case, we will be using the notation, not the number. I have not written 0 because for S sublevel, L is equal to 0, right? But I have not written 0, I have written S, which is the notation for L is equal to 0. And say this is the number of electrons present in the sublevel. Okay, so that is how the electronic configuration is written as per NLX method. Now let me go for the second method called box method. In box method, as we have already seen, orbital is represented as a square or box. Yes, of course. This is the orbital into which we will be adding the electrons. Come on, let us go for that. The same oneness is now represented this way. The first electron in oneness, now the second electron. Then go for the 2s. First electron, the second electron. And finally, this. I told you that you have to fill up one electron each in the orbitals whenever you got degenerated orbitals. That is, whenever you got 3 p orbitals are 5, d orbitals are 7 f orbitals. Is that okay? So that is box method representation. Now, let me also tell you another method called noble gas configuration method. Now, suppose if you want to cut short this, you can do one thing. You know, this 1s2 is in fact the electronic configuration of the noble gas that comes before carbon. We'll all go through that periodic table thing, but for now, you know, this instead of writing this 1s2, you can write the symbol of helium in brackets, the square bracket. So you can just avoid writing 1s2 by simply writing helium, which refers to that 1s2 configuration. Now go for the remaining configuration as it is. Hope this is clear. Only thing is, its preceding inert gas is taken. Its preceding noble gas is taken into consideration. I'll tell you in detail about all these within no time. But for now, remember the preceding noble gas for carbon is helium. I have just written the symbol of helium, He, in square brackets, which refers to this particular configuration, 1s2, because its atomic number is 2. Then the remaining configuration in a normal way using the NLX method. Finally, K, L, M, N method. See this KLMN method. In fact, the KLMN refer to the number of orbits, right? What do you call the first orbit? Yes, it is K shell or K orbit. L is the second orbit, M is the third orbit, N is the fourth orbit, isn't it? So now, how many electrons are there in the first orbit? You got just 2, right? In the first orbit or K shell, you got only 2 electrons. So let us write it this way, 2K. Now, say in the second orbit, go for all the electrons present in the second orbit. How many are there? There are 4 electrons in the second orbit, nothing but the L shell. So let me write 2K, 4L. Hope this is clear. Okay. Check out all different types of writing electronic configuration. The mostly used are the first 2, NLX method and the box method. Check out all these things. Of course, I'm going to give you many more examples, taking the periodic table into consideration. Look at the periodic table. Now, you can actually see horizontal rows, right? If you can see the horizontal rows, look at this. First one, second one, third one, fourth one, fifth one, sixth one, and seventh one, right? Now, these horizontal rows are called periods. Now, the thing that we are looking at is the modern periodic table. The horizontal rows are called periods. How many periods are there? You can see 7 periods, right? Now, there are vertical columns also. See. Vertical, look at this. You got 1, 2, 3, this way, right? Say these vertical columns are called groups. So you can actually see two things. Horizontal rows called periods. Vertical rows, vertical columns called groups. Periods, you got 7 periods. A total of 7 periods are there. Coming to the groups, you can see 18. Check out. Look at the things. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, and then 18th. So there are 18 vertical columns or groups, right? Now look at the old one. First A are the first group. Second A are the second group, but there is some change. Third B, fourth B, fifth B, sixth B, seventh B, and in eighth you got 3 things. Look at this. In eighth you got 3 sub columns. 8th, 9th, and 10th come under 8th B. Then see there is first B, then second B. Very interesting, right? The old one is little complex. You got the things from third B to second B. Check out again. Third B, fourth B, fifth B, sixth B, seventh B. And in 8th B, you got 3 sub columns. Further, 3 things are there. Then you can go for 1B and then 2B. Now again coming back to A, look at this, third A. See the first A, then second A, and here you got your third A. Third A is nothing but 13th group. Fourth A, fifth A, sixth A, seventh A. Of course, this we call it 0 group. Check out the things. All the periods and all the groups are clearly mentioned. So this is my first discussion.
Sir,
Just a second. Just a second. Okay, now I think it is very clear about the number of periods and the number of groups that we have, right? Now coming to the other way around. You know, the first A and second A groups are called S block elements. Okay, first A and second A group elements are called S block elements. Coming to this, look at this area. Third A to 7th A, of course, this is a zero group, or you can say from 13th to 18th. You know, these are called P block elements. Okay. I, of course, have some more interesting things to discuss, but let me just stick to the important things. S block, first A and second A. P block, third A to 7th A and then 0. I mean 13th to 18th. First and second are S block. Coming to this area, from 3rd to 12th, from 3rd to 12th, or 3rd B to 2nd B, you know, these are called D block elements. Okay, D block elements. And coming to this area, which is actually kept at the bottom, you know, these are called F block elements. F. So there are 4 different blocks: S block, P block, D block, and F block. Concentrate on the things. First and second groups come under S block. 13th to 18th come under P block. 3rd to 12th come under D block. And coming to this F block elements, they are in fact the internal part of this D block. You can just check out this here. Look at this. You know, here we generally have only lanthanum. Atomic number of lanthanum is 57. Elements after lanthanum, I mean from 58 to 71. The 14 elements after lanthanum are called lanthanides. Okay, lanthanum is a D block element, but from 58 to 71, the 14 elements after lanthanum are called F block elements. I'll tell you why are these called S and P block, or of course D block, or of course F block later. We are going for all the things one by one. Look at the other thing. You got actinium here. Actinium is 89. Elements after actinium. Look at the element at atomic number 90, thorium. And then finally come here, 103, lawrencium. So from 90 to 103, again 14 elements. These are called actinides. Okay, so you got 14 lanthanides and 14 actinides which come under F block. Okay, so there are 4 different blocks into which the elements are classified: S, P, D, and F. Right. Next. Look at the elements. You have to actually remember the elements in a proper pattern. And today you are going to do that. Coming to the first group, our first A group. Look at this. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Okay. That is all about first A group elements. Coming to the second A, our second group. Come on. Beryllium, magnesium, calcium, strontium, barium, and then radium. Okay. So these are second A group elements. The first A and second A put together are called S block elements, right? Now let us straight away come here, I mean to third A or 13th group. See, in third A or 13th group, you got boron, aluminium, gallium, indium, thallium. Of course, we'll tell you about these. But for now, you just try to remember only up to thallium. So that is all about third A group or 13th group element. Coming to fourth A or 14th group element. Carbon, silicon, germanium, tin, stannum, lead, plumbum. I told you no in yesterday's class. Then going for 50A or 15th group. Nitrogen, phosphorus, arsenic, antimony, and then bismuth. Right? Hope you are following. Coming to 16th group or 60A. Oxygen, sulfur, selenium, tellurium, polonium. See, these are all newly discovered. So we don't generally consider these elements. If you want to consider, you can consider this livermorium also, but just leave it. Okay. We don't have more information about those elements because they have actually been discovered in recent past. Now coming to 17th or 70A group, you got fluorine, chlorine, bromine, iodine, astatine. Right? That is 7th A. Now coming to the zero group elements, or 18th group, you got helium, you got neon, you got argon, krypton, xenon, then radon. Okay. Now, let me just tell you that all the A things, first A, second A, third A, fourth A, fifth A, sixth A, seventh A, and then zero group. Remember these in the form of groups. The group elements. First A group, hydrogen, lithium, sodium, potassium, rubidium, cesium, and then francium. Second A, beryllium, magnesium, calcium, strontium, barium, and radium. Then go for the third A, boron, aluminium, gallium, indium, thallium. Then go for fourth A, carbon, silicon, germanium, tin, and lead. Go for fifth A, nitrogen, phosphorus, arsenic, antimony, bismuth. Sixth A, oxygen, sulfur, selenium, tellurium, and polonium. Then seventh A, fluorine, chlorine, bromine, iodine, and astatine. Then go for the zero group, helium, neon, argon, krypton, xenon, and radon. This is how you have to remember them. Now, keeping all the other things aside, let me go for the D block elements now. Now they have to be remembered in this pattern. So these are the D block elements, right? Now look at the D block elements. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, then zinc. This is how they have to be remembered. You don't try to, of course, remember in this fashion. Okay. D and F, try to remember in this way, this pattern. Right. Now coming to the second transition series, this is the first transition series. Now we are going for the second transition series, starting with yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. So from yttrium to cadmium, the 10 elements come under the second transition series. I've got so many other names, but I don't think you'll be able to understand them now. We'll go for all the other things in the topic periodic classification of elements itself when we go for that after atomic structure chapter. But for now, you just check out the elements, their symbols, their atomic numbers. Okay, now coming to this third transition series, only 57 is what you have to consider. 57 is lanthanum, third transition series. The first element is lanthanum. You know, actually these elements after lanthanum are called lanthanides, right? From cerium to lutetium, they are lanthanides. Let us forget about them for the time being. Go for hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, then mercury. So that is the third transition series. Now coming to the fourth transition series, just consider this element with atomic number 89. You know, that is actinium. Actinium. And those that follow actinium are called actinides. From thorium to lawrencium, they are, of course, actinides. But for the time being, forget about them. Go for this. Rutherfordium. You know, Rutherfordium is also called Kurchatovium. Then comes dubnium, seaborgium, borium, hassium, meitnerium, darmstadtium, roentgenium, copernicium. So this is the fourth transition series. See, in every transition series, you got 10 elements. So there are a total of 40 D block elements, right? How many S block elements are there? You can just check out. Here you got 7 plus 6, 13. And in D block, you got, of course, 40. But here, you know, in 0, of course, D block is ever changing, right? So you generally don't consider this. But you can say here you got 6 plus 25, isn't it? A total of 31 are there. If even these are considered, though not discovered, some are not discovered yet, but still, let me go for 31 without considering these 6. Okay, 6 plus the remaining 5 into 5, 25 plus 6, 31 P block elements. And coming to the F block elements, you know, you got 28, right? Let us check them up. Look at this. Cerium, 58. Praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, chromium, erbium, thulium, ytterbium, and finally lutetium. Lutetium, right? That is 71. So from 58 to 71, you got 14 lanthanides. Now coming to actinides, starting from thorium 90, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and then lawrencium. So from 90 to 103, we got 14 actinides, right? So a total of 28 F block elements are there. Of course, I've got so many interesting points with regard to this periodic table. We'll discuss them from time to time, right? But for now, I hope it is clear. Remember, you need to actually remember the elements in this pattern. S block and the P block. Remember them in this manner. The D block in this. Even the F block in this pattern. You have to remember them for sure. Okay, so this is how you have to remember. Then let me just tell you some more things. You know the elements of this first A group. Of course, except hydrogen and francium, the remaining all are called alkali metals. You just remember the name now because we have a very big discussion with regard to alkali metals. I'll tell you them, all of them later. But for now, remember, the first A group elements are called alkali metals. Coming to the second A group elements, you know, these are called alkaline earth metals. I hope you know that alkali is nothing but base, even here also. Alkaline earth metals. Second A group elements are called alkaline earth metals, right? Now, of course, this is boron family. This is carbon family. No much interesting thing. But coming to this, you know, the fifth A group elements are called nicogens. What do you mean by nicogens? Nicogens are nothing but suffocative elements. Because when these elements are present in larger concentrations in air, we feel suffocated, we feel breathless. So they are called nicogens. Coming to 6th A or 16th group, you know, we call them chalcogens. Chalcogens are nothing but ore farming. Ore is a mineral from which a metal is extracted conveniently and profitable. Generally, the metals are the non-metals. They are generally extracted from their minerals. But from a particular mineral, you can extract the element, the metal or the non-metal, conveniently, I mean easily and economically. Means at a cheaper rate. That particular mineral is said to be ore. Most of the elements occur in the form of their oxides or sulfides. So that is the reason why we call them chalcogens. Coming to the 7th A group elements, look at this. You know, these are called halogens. Halogens are nothing but sea salt producers. If you can remember, sodium chloride, it's a sea salt, also known as rock salt. That is the reason why these elements were given the name halogen. Okay, so 5th group, 5th A or 15th group is called nicogens. 16th A group element, 16th group or 6th A group elements are called chalcogens. 7th A or 17th group elements are called halogens. And one final thing, the 0 group elements or the 18th group, you know, they are called, actually now they are called noble gases. Earlier they were called inert gases. Inert because they generally don't react with any other element. But later they came to know that argon and krypton, of course, sorry, krypton and xenon, of course, react with some other elements like oxygen, fluorine, etc. Earlier, these were thought as non-reactive or inert, so they were given the name inert gas elements. But now they are called noble gases because after in 1962, scientists came to know that krypton and xenon react with elements like fluorine and oxygen and form compounds. So when they came to know this, these were given the name noble gases. Noble means some special, because they react only with the specific elements, not with all. Okay, so look at the names: nicogens, chalcogens, halogens, and of course the noble gas. See, in this periodic table, there is an interesting thing. You can just check the colors. You got metals, you got non-metals, and you got metalloids. Look at this color. Okay, that refers to semi-metal or metalloid. Then this color refers to non-metal and this one refers to metal. I'll give you the list later, but I think now it is clear. Try to remember all these things because they'll be much more useful in future. Now,